Welcome to the Deep Dive. We take your source materials, find the really important insights, and unpack them so you can get up to speed fast.
And today, yeah, we're diving into some fascinating new material. It connects machine learning, especially how it applies in finance, with the Python tools you actually need to make it work.
So think of this as getting you past the buzzwords. We're looking at the core concepts, the real challenges you face, particularly in finance, and the actual code building blocks.
Exactly. We'll hit the main ML ideas, why finance is such a unique beast for these techniques, strategies that actually work, and then, yeah, get hands-on with Python essentials like NumPy and Pandas.
Okay, sounds like a great plan. Let's unpack this.
So let's start right at the beginning. What actually is machine learning? The sources give us that, that standard definition from Tom Mitchell.
Right, the E, T, and P thing.
Exactly. A computer program learns from experience E for some task T, using a performance measure P if its performance P on task E improves with more experience E.
Okay, so E is the data, the experience, what it learns from.
Yep. The training signal.
T is the job you want it to do, predict something, classify something.
Right. The specific task.
And P is how you know if it's doing a good job. The score, basically.
Precisely. How you measure success or, well, failure. And this framework immediately shows you ML isn't just one thing, right? It really depends on the task, the data you feed it, and how you define good.
And the sources seem to really emphasize a probabilistic view of ML. Why is that so important here?
Ah, that's key. Especially in finance, dealing with uncertainty. This view means we treat things we don't know, future prices, model parameters, whatever, not as fixed points, but as random variables. They have probability distributions.
So thinking in terms of likelihoods, ranges, not just the answer is X.
Exactly, which
Okay.
feels much more realistic for markets, doesn't it? The sources give two big reasons for this approach. First, it's mathematically the optimal way to make decisions when things are uncertain. You can quantify risk properly.
Makes sense. And the second,
Second, and this is maybe even bigger picture, it gives us a common language. It connects ML to statistics, physics, engineering. As one quote put it, almost all of machine learning can be viewed in probabilistic terms. So it's fundamental.
okay, so it's a core way of thinking, not just one technique. Within that, what are the main types of ML the sources cover?
Well, the most common one is supervised learning. That's where you have inputs and you know the correct outputs for your training data. It learns the mapping.
Like, here are company financials, and here's whether they defaulted or not. Learn the pattern.
Precisely. Learning from labeled examples.
Mm-hmm.
Then you've got unsupervised learning. No labels here. The goal is finding hidden structure or patterns in the data itself.
Things like dimensionality reduction, finding the core drivers.
Exactly. The sources mention factor analysis, probabilistic PCA,
Yeah.
trying to find those latent factors underneath. It can get more complex with nonlinear models and neural networks, but that's harder to fit well.
Okay, and there was one more, self-supervised.
Yeah, that's a more recent idea. It's clever you take unlabeled data and kind of automatically create a supervised task from it. Maybe predict a missing word in a sentence or a mask part of an image.
Interesting. So creating its own labels, in a way.
Sort of, yeah.
Yeah.
Okay, so that's the landscape. But just knowing the types isn't enough. Applying ML, especially in the real world, throws up big challenges. One huge one the sources hit on is defining that P, the performance measure.
Defining success, the loss function.
Right. Designing that loss function. It's incredibly hard to perfectly capture everything we care about, all the nuances, the unspoken rules, the side effects in one mathematical formula.
And if you don't get that right, that leads to reward hacking, doesn't it?
Exactly. The machine does exactly what you told it to optimize, but finds a shortcut or exploit you didn't intend, hitting the metric but missing the point.
Which connects to that bigger issue, the alignment problem.
Yes, a really critical area. How do we make sure that what these powerful algorithms optimize actually aligns with complex human values and goals? That's where you get into AI ethics, AI safety. Really important stuff.
It's not just about making it work, but making it work right and safely.
Couldn't agree more. One approach the sources mentioned to tackle alignment is inverse reinforcement learning, or IRL.
Okay, how does that work?
Instead of you telling the machine the reward function, you showed examples of, say, good human decisions or behavior. And the machine tried to work backwards to figure out what reward function that human must have been implicitly optimizing.
So it learns our goals by watching us.
That's the idea. But, and it's a big but, the sources point out, what if the human behavior it watches is biased?
Ah,
Then it learns the bias.
Exactly. It learns what was done, maybe including all the flaws and biases, not necessarily what should have been done ideally. Garbage in, garbage out, potentially.
So the data quality, the example quality is paramount again, always. And the sources briefly touch on two different sort of philosophies too. AGI, artificial general intelligence systems that could potentially reason and act autonomously across many domains,
Sci-fi stuff, maybe.
perhaps, versus IA, augmented intelligence, using AI tools to make humans smarter, more effective, better decision makers. For finance right now, IA often feels like the more immediate practical focus.
Okay, that makes sense. Enhancing human experts. Now, let's pivot specifically to finance, applying these ML ideas there. The sources say it's got its own unique set of really tough hurdles.
Oh, definitely. Financial markets are, well, notoriously noisy. The signal-to-noise ratio is incredibly low. Finding genuine predictive patterns amidst all the randomness is just fundamentally hard.
It's not like image recognition where a cat looks mostly like a cat. Market dynamics shift, regimes change.
Exactly. And maybe the biggest single constraint, the sources hammer home, data, specifically the lack of volume.
Really? You think finance, you think data?
Yeah, but compare it to, say, Google or Facebook's data on user behavior, or image data sets with billions of examples. Traditional financial data, even 100 years of daily prices, is tiny in comparison. Quarterly reports, even smaller.
That's a great point. A century of daily data is only, what, 25,000 points per asset? Peanuts in the ML world?
Right, and even with alternative data,
Yeah.
new Sentinel satellite stuff, it's still often not the sheer scale you see elsewhere.
And why does that sheer volume matter so much for ML? The sources had a strong take on this.
They did. They argue that the power of many modern ML algorithms, especially the complex ones like deep learning, is massively driven by just having tons and tons of data. Often, a simpler algorithm fed a huge data set will crush a super fancy model trained on limited data.
So data quantity can actually trump model sophistication.
Very often, yes. It's like fuel for the engine. More data lets the models find subtler patterns without just memorizing noise.
And that lack of data makes testing harder too, right? Overfitting.
Absolutely critical point. You need enough data to split cleanly into training, validation for tuning, and a completely separate untouched test set. Without that, you're fooling yourself. You find patterns that work in your sample but vanish out of sample, that's overfitting.
Finding fool's gold in the data.
Precisely. You need enough data for robust cross-validation, reliable hyperparameter tuning, stress testing, all essential for building something trustworthy.
Okay, so finance is tough. Low signal, relatively little data compared to other fields, high complexity. Given all that, how do you make ML work effectively? What strategies do the sources suggest?
Well, several things. One approach comes after the model spits out a prediction, using techniques for ex post explanation, like SHA values.
Ex post. So explaining it after the fact.
Yeah, you try to understand why the model made that specific prediction. Like, okay, it predicted higher default risk for this company. Why? And the explanation might show, well, the biggest factor was its high leverage ratio.
And that's where the human expert comes back in.
Exactly. An experienced analyst looks at that and says, okay, high leverage, increasing default risk. That makes sense financially. But if the explanation points to something bizarre, or maybe the model says high leverage, decreased risk, that's a huge red flag. Maybe the model's broken or just overfit.
So you're using the explanation to sanity check the model's reasoning and not just blindly trusting the output.
Yes, it's a debugging tool as much as an explanation tool. Then there's work you do before training, feature engineering.
Choosing the right inputs.
Critically important. This is pure domain knowledge. You need to select and maybe transform input variables that you have good reason to believe should have a causal link to what you're trying to predict.
Like using profit margins to predict earnings surprises makes sense. Using, I don't know, the number of letters in the CEO's name, probably not.
Exactly the kind of thing. The sources give that example. Using something irrelevant, like the CEO's first initial, is asking for trouble, likely to lead to spurious correlations.
So ML doesn't replace financial common sense. It has to be guided by it.
Absolutely. And speaking of common sense, another massive pitfall is data leakage. This is subtle, but deadly.
Leakage, like future information getting into the past.
Precisely. Information that you wouldn't have known at the time you were making the prediction somehow contaminates your training or validation data. The classic example is using, say, revised economic numbers that weren't available back then, or non-public information.
Your backtest looks amazing because your model secretly has a crystal ball.
Exactly. A basic but crucial defense is putting a time gap, a buffer zone, between your training data period, your validation period, and your final test period. Don't let them touch.
Building a firewall against seeing the future.
Yeah. The sources really stress this. Common sense still needs to prevail. You have to think hard. What information was really available at that specific point in time?
Makes sense. And the final challenge mentioned was the implementation gap.
Ah, yes. The gap between a great-looking backtest and what's actually possible or profitable to trade live.
Like a strategy that relies on trading huge volumes of tiny, illiquid stocks.
Exactly. The transaction costs, the market impact of your own trades.
Yeah.
It can kill the theoretical performance. And since ML models can sometimes have high turnover, trading frequently, this problem can be even worse for them, especially in less liquid markets.
A reality check for any quantitative strategy, but maybe amplified for some ML approaches.
It can be, yeah.
Okay, so we've got the ML concepts, the finance-specific hurdles, the strategies. Now, how do you actually do this stuff? Let's talk tools. The sources dive into the Python building blocks.
Right. Starting with the absolute basics, Python's core data types, integers, int, floating point numbers, float for decimals, and strings, scr for text. And Python's dynamically typed, remember. The type is figured out on the fly.
Flexible. And for finance, precision matters with numbers, right? The sources mentioned something about floats.
Yeah, standard floats can have tiny precision issues that sometimes add up. For really sensitive calculations, Python has a decimal module that gives you arbitrary precision. Good to know it's there if you need it.
Okay. Then beyond single values, we get into collections of data, tuples, lists.
Right. Couples, defined with the parentheses. They're ordered, simple, but the key is they're immutable. Once you create a tuple, you can't change its contents.
Fixed sequences. And lists. Square brackets.
Lists are the workhorses. They're ordered, zero index like tuples, but they are immutable. You can add elements, append, extend, insert them, remove, pop, change them. Much more flexible for things that need to grow or change.
And you can loop over them easily, slice them up to get parts. The sources mention list comprehensions too.
Yeah, a concise way to create lists. XX for X in range 10 gives you squares, for example. Very Pythonic. And briefly, there are functional tools like map, filter, lambda functions for operating on lists compactly, though we'll see NumPy often replaces these for speed with numbers.
Got it. Then dictionaries, curly braces.
Dictionaries, or dicts. These store key-value pairs. Think of a real dictionary. The word is the key. The definition is the value. They're unordered. Well, order is guaranteed in recent Python versions, but you usually don't rely on it. And mutable. Super fast for looking things up by a known key, like getting data for a specific stock ticker.
Useful for configuration, structured data. And finally, sets.
Sets, also using curly braces sometimes, or set. They store only unique elements and they're unordered. Great for checking if something is in a collection quickly or doing mathematical sets of unions, intersections, differences, like finding stocks that are in both the S&P 500 and a list of tech stocks.
Okay, so those are the Python fundamentals. But for the heavy lifting in finance, especially with numerical data, the sources point squarely at two libraries, NumPy and Pandas.
Absolutely essential. NumPy brings us the end array, the n-dimensional array. This is purpose-built for efficient math on blocks of numbers, vectors, matrices, you name it. It's way, way faster and more convenient than using nested Python lists for this stuff.
Faster because of
vectorization. NumPy arrays have built-in methods like sum.std. But the magic is doing math directly on the arrays. Array2, np.securrt array. NumPy runs highly optimized C code under the hood to apply that operation to every element.
So instead of a slow Python loop, it's one fast, optimized operation on the whole block of data.
Exactly. That is the core performance principle for numerical work in Python. Avoid explicit loops, use vectorized operations.
Got it. Vectorization is king.
It really is. NumPy also has broadcasting rules for how operations work between arrays of different but compatible shapes, like adding a single number to every element of an array. And it provides universal functions, or ufuncs.
Ufuncs.
These are functions like np.syn, np.exp, np.log that work element-wise on entire NumPy arrays. You need these because the standard Python math.syn doesn't know how to handle an array, only a single number.
Right, use the NumPy version of the function for NumPy arrays.
Always. The sources even mention low-level details, like memory layout C order versus Fortran order, which can impact performance for very large arrays depending on how you access them. Shows how deep the optimization can go.
Wow, okay, so NumPy is the foundation for fast numbers.
Yeah.
Then Pandas builds on that specifically for financial data.
Exactly. Pandas was created pretty much for dealing with labeled time-indexed data like financial time series. It took inspiration from R's data frames. The main tool is the data frame.
The data frame, like a spreadsheet or a database table, but way more powerful.
That's a good analogy. Rows are often observations like dates or timestamps. Columns are variables, prices, volumes, indicators. It has an index. You can create them easily from dictionaries, lists, NumPy arrays. And selecting data is very flexible using labels or positions.
And real financial data is missing values.
Pandas handles missing data, usually represented as NaN, not a number,
Right.
really well. Most operations just skip NaNs by default, which is often what you want. Huge convenience.
Definitely. And for time series.
The datetime index is brilliant. Pandas makes creating time-based indexes super easy with functions like pd.datarange, specifying start, end, frequency, daily, monthly, business days, minutes, whatever you need.
And like NumPy, data frames have tons of built-in methods for analysis.
Oh yeah, sum.doc describe for quick summaries, .com_sum for cumulative sums. Lots of statistics. And they work seamlessly with NumPy ufuncs too. Plus, easy plotting, often just .plot on a data frame or series, gets you a decent chart quickly via matplotlib integration.
Very handy for visual checks. And the group B thing.
Super powerful. It lets you split your data into groups based on some criteria, like industry sector or year, apply a function to each group, like calculate the mean return,
Yeah.
and combine the results back together. Think pivot tables in Excel or SQL group P by Y clauses. Essential for summarizing categorized data.
Okay. Theory's good, but the sources had practical examples using pandas, right?
They did. Showed how easily you can grab data, say from Yahoo Finance, directly into a data frame using helper libraries.
Nice. And the log returns example, that seemed important.
Oh, that was the killer demo for vectorization in Pandas. Calculating log returns using a standard Python loop over the data took, in their example, something like 452 milliseconds.
Okay, nearly half a second.
And they did the exact same calculation using Pandas vectorize.shift method to get the previous day's price and NumPy's np.log function, the time, 1.52 milliseconds.
Whoa, that's almost 300 times faster.
Yep. That single comparison tells you almost everything you need to know about why you use Pandas and NumPy for data analysis in Python. Performance isn't just nice, it's absolutely necessary when data gets large. And the vectorized code is usually shorter and cleaner too.
Vectorize, vectorize, vectorize.
Got it. It's the mantra. The sources also showed rolling calculations, rolling averages, rolling correlations, which are bread and butter for time series. Easy in Pandas, pedo.rollingmean, peyote.rolling core. Their example plotted the rolling correlation between the EuroSOX 50 index and the VSOXX volatility index, clearly showing that changing negative relationship over time. Very insightful.
And it handles high-frequency tick data, too. That often has irregular timestamps.
It does. You might end up with an irregular time index, but Pandas can handle it.
Yeah.
And there's a great method called resample.
A resample.
Yeah, it's for converting time series to a different frequency. You could take irregular tick data and aggregate it into, say, regular 5-minute bars by taking the average price or max or min or whatever within each 5-minute interval. Really useful for standardizing high-frequency stuff.
Wow, okay. We have definitely covered a lot of ground here. Started with those core ML ideas, that probabilistic view.
I dug into the real, the tough challenges of using ML in finance. The noise, the data limitations, making sure models don't just work on paper but in practice,
Yeah.
avoiding things like data leakage.
Right, and the strategies to deal with that feature engineering, using explanations like SAP, being careful with testing.
And then we got into the tools, the basic Python structures, but crucially NumPy for the fast numerical horsepower with its arrays and vectorization.
And Pandas, the absolute workhorse for financial data analysis, especially time series, making things convenient and performant, again, thanks to that vectorized foundation.
It really paints a picture, doesn't it?
Yeah.
Success here isn't just knowing ML algorithms. It's this blend, understanding the ML theory, having deep financial domain knowledge to guide it, and mastering the practical tools like Pandas to actually implement it correctly and efficiently.
Absolutely. And thinking back to those challenges, particularly things like the alignment problem, reward hacking, the risk of bias creeping in from data,
Yeah.
it makes you think about the responsibility that comes with using these powerful tools.
Mm-hmm.
So here's a final thought for you to chew on. Given everything we've discussed, the power of ML, the specific difficulties in finance, the critical importance of data and validation, and the capabilities of tools like Pandas, how can a really strong foundation in both the financial domain and the careful, thoughtful application of these programming tools help us build not just models that perform well on paper, but systems that are ultimately more reliable, more transparent, and more aligned with what we actually intend them to do in the complex world of finance?
That's a great question to ponder as you continue your own deep dive into this fascinating intersection of fields.